Hello guys, this is Hui from Lab, Mississippi State University. Today, we'll dive into the world of the UV-Vis spectroscopy. What is beyond the Beer-Lambert law that we already know? So, here is a little bit background of our research group. We intensively focus on the interaction of light and matters, including polarized light interaction and advanced instrumentation design. At the moment, we are also progressing an educational project on enhancing student critical thinking and shedding new light on the famous Beer-Lambert law. With that being said, here are our selected scientific publications focusing on light and matter interactions. The first two are designated for enhancing student education. The second one is under minor revision by the Journal of Chemical Education. Therefore, in this video, we will discuss about what is beyond the Beer-Lambert law, what is truly behind the UV-Vis spectrum that you might have taken yesterday in the lab. And I will introduce you guys 5 types of common samples: pure scatterer, pure absorbers, simultaneous absorber scatterer, simultaneous absorber emitters, and lastly, the most complex one, simultaneous absorber, scatterer, and emitters. Let's start with current UV-Vis education. Shown here is a schematic of a commonly used double-beam UV-Vis spectrophotometer. In its setup, light from a source passes through a monochromator and is then split between a reference cuvette and a sample cuvette. A chopper alternates the light path, and the resulting signals are directed to a single detector. According to the Beer-Lambert law, absorbance is calculated as the negative logarithm of the ratio between the transmitted intensity, IT, and the incident intensity, I0. This approach relies on 2 key assumptions. First, the light attenuation occurs solely due to the process of absorption. Secondly, that the transmitted intensity is equal to the detected light intensity. Based on these assumptions, the UV-Vis spectrum is commonly interpreted as a direct measurement of the sample absorbance. However, in real-world samples, light attenuation can also occur through other mechanisms, such as scattering, which reduces the intensity of light that makes it through the samples. Additionally, the UV-Vis detector cannot distinguish between the transmitted light and any other photons reaching it, such as scattered or emitted light. Both of these can lead to false interpretation of the UV-Vis measurement data. Let's dig deep into what type of samples that we encountered based on the photon-matters interaction. To visualize how real samples interact with light, here we use a green laser beam passed through 6 different types of samples. Each is placed in a single cuvette. The beam is then struck a black screen behind the samples, allowing us to observe how light is altered. Sample A is just water, a base light, with no significant absorption, scattering, or emission. The laser passes straight through with minimal change. Sample B is a pure absorber, potassium permanganate. Here, the laser beams becomes noticeably dimmer. This is because the sample absorbs the light, converting its energy primarily into heat. This represents a textbook absorption process. And in sample C, we have a pure scatterer, white polystyrene nanoparticles. The light isn't absorbed, but tiny suspended particles cause the laser beam to scatter into multiple directions. The forward beam loses intensity, not because the energy is lost, but actually because the light is being redirected away from the beam path. Sample D both absorbs and scatters light, red polystyrene nanoparticles. The beams is attenuated due to a combination of these processes, illustrating how multiple mechanisms can work together to reduce the transmitted energy. In the sample E, rhodamine 101, the sample is not absorbs light but also re-emits part of it as fluorescence. You will notice that the beam again dims, but in this time, some of the absorbed green light is emitted back as orange fluorescence. This means that the light isn't entirely lost, but is actually being transformed and re-radiated. Finally, sample F, the mixture of rhodamine dye with polystyrene nanoparticle, which combines all three effects: absorption, scattering, and emission. The laser beam is attenuated through both absorption and scattering, and a portion of the absorbed energy is re-emitted as fluorescence. So, in all of these cases, you can clearly see that the intensity of the laser spot on the screen is diminished compared to the water sample. This illustrates how light attenuation occurs through absorption, scattering, or both. And why assuming a direct link between detected intensity and absorption alone can be misleading in complex sample. Let's start with how pure absorber behaves inside a UV-Vis spectrophotometer. A beam of light with initial intensity I0 enters the sample. As it passes through, a part of that light is attenuated due to absorption. The remaining light exits the cuvette and reaches the detector, which measures as the detected intensity ID. The instrument is then calculate the extinction using the negative logarithm of the ratio between the detected and the supplied intensity. In this case, because light attenuation occurs solely through absorption and no further photons reach the detector, then the detected intensity is equal to the true transmitted intensity. As a result, the measured extinction directly corresponds to the sample absorptions. Under these ideal conditions, the extinction increases linearly with concentration, following the Beer-Lambert law. Now, let's take a look at pure scatter sample. As light enters the cuvette, it is not absorbed, but instead, it is redirected. This causes a reduction in the intensity of the forward transmitted beam. The UV-Vis spectrophotometer, they still calculate the extinction using the same equation. However, there is still a crucial difference here. The detector does not only receive the forward transmitted light, it can also detect some of the scattered photons depending on their angles and the accepted angle of the detector's optics. This means that the ID they can include both the true transmitted light and a portion of scattered light. As a result, the extinction value measured by the instrument may underestimate the actual scattering extinction of the sample. Furthermore, the amount of scattered light that reaches the detectors varies depending on the nature of the scatterer, such as its particle size, the optical properties, and also on the concentration. As you can see, at low concentration, the scattered light contribute to the ID is minimal. So under these conditions, the measured extinction closely reflects the true scattered extinction and still show the linear behavior with the concentration. But as the concentration increases, more scattered photons reach the detector along the side of transmitted light. This causes deviation from the expected linearity and ultimately a breakdown of Beer-Lambert law behavior in purely scattering systems. We're now heading to simultaneously absorbing and scattering samples. In this case, the sample both absorb and scattered light. As the incident beam enters the sample, a portion of photon is absorbed, just like in the pure absorber case, and another portion is scattered in various directions. The UV-Vis instrument once again calculates the extinction based on the negative logarithm between the ratio of the detected intensity and the supply intensity. However, the detector now receives a mix of two types of photons. Firstly, the remaining of unabsorbed and unscattered transmitted light. Secondly, a portion of the scattered photons reaching the detector. As a result, the scattered photons reaching the detectors along with the transmitted intensity and the detected intensity is elevated compared to what would be expected from the absorption and scattering alone. This will lead to an underestimate of the total light attenuation by absorption and scattering. And at low concentration, where the scattering photons interference is minimum, the extinction measurement may still appear linear. Keep that in mind. The extinction measured here is actually a combination of both the absorption and the scattering extinction of the sample. Thus, as the concentration increases, the detected signal becomes more and more contaminated by the scattered light, leading to deviation from the Beer-Lambert law. The next type of sample is simultaneously absorbing and emitting sample. This sample behaves differently. It can absorb part of the incident light, but instead of just converting that energy into heat, it actually re-emit a portion of that as fluorescence. The detectors once again record all the light reaching it. So in this case, the detected intensity ID includes first the transmitted light after the absorption and the emitted fluorescence light, which is often at different wavelengths. Because the UV-Vis spectrophotometer, it is not designed to separate these contributions. It interprets this mixed signal as a transmitted light. So, this artificially lowers the calculated extinction since also the emitted photons reach the detector. And at low concentration, the contribution of emissions may be negligible, allowing the measured extinction to be nearly equal to the actual absorption extinction of the sample and follow linear behavior with the concentration. But as the concentration increases, the interference of the emitted light on the detected intensity becomes more significant, again causing deviation from the Beer-Lambert law that we already know. Now we're heading to the final case. In this one, your sample is simultaneously absorbed, scattered, and also emits some light. Some of the incident photons are absorbed and converted into heat. Some of them are scattered in all directions, and some of them already emit as fluorescence. As with all previous cases, the UV-Vis instrument does not discriminate among these photon types. It simply detects whatever light reaching it and calculates the extinction. This means that the ID now can include the transmitted light, the scattered light that happens to reach the detector, and the fluorescence photons emitted by the sample. At lower concentration, similar manner to the previous samples, the measured UV-Vis extinction will reflect a combination of absorption and scattering extinction and follow Beer's law since the interference of scattered and emitted photons on the detected intensity is negligible. However, as the concentration increases, scattered and emitted photons can significantly distort your measured extinction in a similar manner to the samples discussed previously. Therefore, the nonlinearity relationship between the sample concentration and the UV-Vis extinction at higher concentration, making it nearly impossible to interpret the spectrum. This example highlights how real-world samples can break down the assumption underlying the Beer-Lambert law, especially in the presence of scattering and fluorescence. We've been discussed how different types of samples can interact with light. Now, let's take a look at real experimental data. The first column shows the UV-Vis extinction spectra for 3 sets of samples, each with a range of concentration. Figure A shows potassium permanganate, a purely absorbing sample. As concentration increases, the absorption peaks become stronger, and the spectra maintain a consistent shape. In Figure C shows the spectra for plain polystyrene nanoparticle, which is a pure scatterer. We see an overall increases in the extinction across all wavelengths, but the spectral shape is mainly due to the attenuation of light by scattering. There is also noticeable flattening and distortion at higher concentration. In Figure E is for anthracene, a fluorescence dye. With increasing concentration, extinction increased initially, but the spectra eventually flattened due to self-absorption and fluorescence interference. The second column shows how extinction varies with concentration at a selected wavelength for each corresponding system. Figure B for potassium permanganate, it shows a nearly perfect linear relationship just as predicted by the Beer-Lambert law. But in contrast, Figure D for polystyrene nanoparticles, it shows an initial linear trend that can be deviated at higher concentration. This non-linearity reflects the increasing impact of scattered light reaching the detector. Finally, in Figure F for anthracene, also shows a deviation from linearity at higher concentrations due to fluorescence emission. These results clearly demonstrate how the presence of scattering and fluorescence can compromise the linear dynamic range of the measurement of the sample in the UV-Vis extinction measurement, and they can induce spectral distortion as the concentration of the sample increases. So, to explore this optical behavior firsthand, here is a simple laboratory experiment that you can perform using a UV-Vis spectrophotometer. Prepare 4 different types of samples, each representing a different optical behavior. First is potassium permanganate, a pure absorber. Secondly, white polystyrene nanoparticle, which is a pure scatterer. Third, red dye polystyrene nanoparticle, which both absorb and scatter light. Finally, rhodamine 101, a fluorescent dye that absorbs and emits light. For each type of the sample, prepare a concentration series as shown in the table. This concentration range are carefully chosen to cover low to moderately high optical density. As I've shown it here, once you have the sample, you can measure the UV-Vis spectrum for each one, let's say from 300 to 750 nanometers. Then, you can plot the measured UV-Vis extinction at peak wavelength versus the concentrations. This will allow you to visually compare the linear dynamic range across different types of samples. You will then observe that while the potassium permanganate data follows a nearly perfect linear trend, the other samples start deviating from linearity at different concentration, it depending on whether scattering, fluorescence, or both are present. This hands-on exercise can reinforce a key lesson. Not all the extinction is due to absorption, and interpreting UV-Vis data without considering scattering or emission effect can lead to inaccurate conclusion, especially for real-world and complex samples. So, what is the bottom line? Actually, this paper is a call to action. Let's break free from the oversimplified notation of UV-Vis as just absorbance. In reality, every measurement we see is actually a combination of absorption, scattering, and possibly fluorescence. The key takeaway here is pretty simple. If we recognize that real samples rarely behave like ideal Beer-Lambert law absorbers, we will then design a better experiment and teach future scientists to approach the UV-Vis with the accuracy it deserves. This could mean the big leap forward in the nanotechnology, the photochemistry, and so many fields that rely on accurate spectral data. Thank you guys for tuning in. I believe that this novel approach on the UV-Vis measurement would benefit the science field and also the student education. Lastly, I would say thanks to my advisor, Dr. Zhang, for such an excellent guidance throughout this project and the NSF funding supporting the work as well. So if you have any question, please drop them in the comment and explore our website for more insight to the world of light and matter interaction. If you enjoyed this journey, please hit like, subscribe, and stay curious. I will see you really soon.